All right, this is October 30th, 2020. This is Physics CP lecture on forces at an angle. Forces at an angle. I'm going to lead off by reviewing from math class about triangles, right triangles in particular. So first thing is I'm going to draw a right triangle, just a generic one that says, oh yeah, they go off to the right. Haha, kind of a joke. And they form a right angle, a 90-degree angle, someplace there, I've marked it. And finally, we label these things several different styles of ways of doing this. One way is to refer to everything that goes to the right as being the positive x-axis, everything that's going towards the top of your page as being the positive y-axis. So that's the coordinate system that we tend to be using. I need audio. I need a visual. I'm not sure what I need. I have three different views going on right now, and one of them suggests you. Okay, here's a question. Let me do it this way. Yes or no? Can you see the tip of my pen right now? You can. Wow. Okay, so that's very interesting. If you guys haven't pinned to this thing, then maybe you should. All right, so the point of view is often from this corner of the triangle, but be aware, you might be from the other side. I'm going to call this reference angle theta. So there's the Greek letter for theta. The side nearest this reference angle is called the adjacent side. We might label it with some letter like A. We could also call it just the x value of it. Okay, so I could call it A, I could call it x. This side over here is known as the opposite side. Welcome back, Siddharth. You could call it B. Other style would be to call it Y. And don't ask why. I'm telling you why. That's okay, Siddharth. You think your internet's slow. You should see me without caffeine. All right. So, still looks focused. Okay. This longest side, always the longest side, is called the hypotenuse. Hypotenuse. And one way of referring to it is to call it the C side. So we have A, B, or C. And the other way to refer to it would be to call it R, the magnitude vector, R. Great. You've allegedly all been exposed to this in your math courses. Is there anyone who's not seen this? Excellent. So you probably have atrophied on your skills. I do this every day, and I've been doing it for decades. So for me, this is like breathing. Oh, yeah, here's how you do this. Here's how you get that. For you, well, let's review. The first thing that helps you be successful is Pythagorean's theorem. Now, maybe I can't spell it, but I could certainly write it as c squared, the length of the hypotenuse squared, is equal to the leg A squared plus leg B squared. Great. Using the alternate labels, I would write this as r squared is equal to x squared plus y squared. Okay, so one way is sort of like beginning, and the other way is a little bit more, I don't know, mature, evolved, advanced way of notation. Okay, so there's that. Now, the trigonometric ratios. These are dimensionless numbers that for right triangles, we've gotten to know very, very well and say, okay, whatever, and by the way, whatever units we're in, it's got to be exactly the same units for all three sides. I can't have one unit be a force and another side be a distance and another side be a speed or a velocity or an acceleration. No, 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 no. If one of these is a force, then all three sides have to be a force. If one leg is a velocity, all three sides have to be velocity. If one side is an acceleration, all three sides of this triangle are accelerations. You cannot mix units on this triangle. But whatever those units are, the trig functions are the ratios of one side to another. And the three ratios that we're going to be using are the ones that you memorize with SOHCAHTOA. So you've got SOH, which means the sine of that reference angle theta is equal to the ratio of the opposite side divided by the hypotenuse, hence the SOH. Sine is opposite divided by hypotenuse. Of course, the opposite side, I notated that as being B over C, but I also wrote it as being Y divided by R. So whichever style you want to use for labeling these things, that's fine. I myself tend to be an XYR type of person because sometimes I work in polar coordinates, and that's a perfect lead in to working in polar coordinates. You work with whatever notation you are most comfortable with. COA is the shorthand way of saying the cosine of that reference angle theta is the ratio of the adjacent side divided by the hypotenuse. And using my choices for notation here, that means I could label it as A divided by C, or I can call it X divided by R. All the same thing. And yes, there's a third one, TOA, the tangent function. TOA. The tangent of the reference angle is the ratio of the opposite side from the reference angle divided by the adjacent leg to the reference angle. So no hypotenuse. So in my notation, I guess I could label that as B divided by A, and I can also label that as Y divided by X. My 8th grade math teacher used a mnemonic memory device that said, Oscar had a hairy old aunt. I don't know if that's of any use to you. Oscar had a hairy old aunt. Ugh, what a picture. But that was his way of trying to have us memorize that the sine of an angle is the ratio of the opposite leg divided by the hypotenuse. The cosine of a reference angle is the ratio of the adjacent leg divided by the hypotenuse. And the tangent of a reference angle is the ratio of the opposite leg divided by the adjacent leg. Great. So how would you do this using a calculator? Most of you, along with me, are using Texas Instrument brand calculators or graphing calculators or programming calculators, whatever. If you don't, if all you have is a basic calculator, as long as it has the trig functions, sine, cosine, tangent, you're good to go. If you have a Casio, they have it. If you don't have a calculator that can do trig functions, you're going to have to go online. And they exist. You just type in, ask Lord Google, what is the sine of so many degrees? I'm sure Lord Google would be happy to tell you. In math class, you guys had to study about cotangents and secants and cosecants. We don't need that here in this physics course. All we need is what I've written down so far. So there's the good news. There's nothing more than this. The bad news is, do you know how to do this? Can you practice it? Can you solve physics problems with this stuff? Interesting. I'm checking my notes for yesterday and saying, all right, what shall I do? All right, let's do a calculation. Let's say that I have side A. Okay, so example. Side A is 12 units. And the units can be anything, right? Doesn't matter. I'll say meters, 12 meters. Meanwhile, the hypotenuse, C, let's say that's 13 meters. My question for you, what is the length of side B? All right, try that one. In principle, this is a math review question, and I don't even need to tell you how to go find B. I will say the way to do it is currently being displayed. If I knew A and I knew C, how would I find B? And of course, as an alternate way of writing this, I could say, if I knew X and I knew Y, I'm sorry, R, if I knew X and I knew R, how would I find Y? Okay, time to start randomly picking on students. I'm going to start off with Katie. Katie, what'd you get? No units? Yes. And I suppose technically I could argue that this is 2 sig figs, that's 2 sig figs, so I'll call this 2 sig figs as well. 5 meters. And Katie, how did you get that? Interesting that you said c squared is 169 and c squared is 144. Yes, you deserve to lose points for such a. I would have been happy if you'd merely said, "Oh, I used Pythagorean's theorem." That would have been an adequate answer right there. But if you're going to try to actually use numbers, you should have said 169 is 13 squared. 144 is 12 squared. 169 minus 144 is 25. And the square root of 25 is 5. That's what you meant to say, isn't it, Katie? Yes, yes. Good job, Katie. All right. So now I have another question for you students. And for this one, how do you get it? Okay, the question is, what is the angle value in this case, the reference angle? And for that one, I didn't really get into it, but on your calculator, you can't just type sine of something. You have to ask it, what is the angle whose sine is something. So if I start off, I'll just pick any one of these three. If I start off by saying the sine of the angle is opposite over hypotenuse, then the reference angle is the inverse sine of opposite over hypotenuse. Yikes. Joseph, how do you want me to notate that? Do you want me to write op over hype, or do you want me to write b over c, or y over x? Okay, opposite over hypotenuse. The inverse, let's see, theta is the inverse cosine of adjacent over hypotenuse. And theta is the inverse tangent of opposite divided by adjacent. So how do we do this on a calculator? A mistake would be to use the 1 over x button, the x to the minus 1 button, or 1 over x. That's not what this is saying. This is saying, look, I'm going to give you, calculator, the ratio. Please, in return, tell me what angle that corresponds to. To activate the inverse trig function on a TI model, you would press the second button. And now, when you press a trig function, boop, and you zoom in and look at it, something I'd have to do like this, just for you, and then let it autofocus, and then dim this thing so you can see it, and autofocus so you can see it. There. Now it says, oh, I'm going to find the inverse sine. And whatever I type in, as long as it's a number between -1 and +1 exclusive, it'll give me an answer. Huh. So if I type in, for example, 0.5, which is not part of this problem, and press enter, it says, oh, well, hopefully it'll say 30 degrees in that case. What if it doesn't? Then you should worry about what mode you are in. The mode button for us in this course should be set for degrees, not radians, and not gradients. Okay, so if you're on a TI calculator, press the mode button, which is near the top. It's one of the top two rows. And verify that you're set for degrees, which is flashing right now on my screen. Okay, so that's how you take the inverse of a trig function. And my next volunteer is Matthew Baldovino. What did you get as the value of the reference angle? Ooh, 6 points off from you just for that. The question is, what is the value of the reference angle when the adjacent side has length 12 meters, the opposite side has length 5 meters, the hypotenuse has length 13 meters? Under those conditions, what is the value of the reference angle? All right, and Jacob, Matthew, do you agree with that? And hence I have job security as a teacher, because that's really, really wrong. I'm not asking for the ratio, I'm asking for the angle. And to get that answer, you must take the inverse of one of these three trig functions. You pick which one you want to use. And you must be in units of degrees on your calculator to get it correct. So, Matthew, do you want to try responding to that one again? It would seem that way to me as well. What do you get this time? Oh man, Jacob, do you agree with that? Uh, um, what do you get, Jacob? Interesting. So you have basically the complement of the answer that Matthew gave. All right. So Eric, resolve this dilemma. We've got two students, two answers. What's your answer? 0.5. What is with? Where do you come up with stuff like that from? It's 22.6 degrees. Now there's three ways you can get the answer. You could take the inverse sine of 5 divided by 13. You could take the inverse cosine of 12 divided by 13. You could take the inverse tangent of 5 divided by 12. But as Jacob might be able to explain to you, if you take the inverse tangent of 12 divided by 5, you're going to get the opposite. You're going to get the complementary angle instead of the one that we want. They sometimes call this angle phi, just to give it one of the other names. Okay, so phi would be 12 divided by 5. Theta would be 5 divided by 12 for the tangent function. Same thing for sine and cosine. The sine of phi is 12 divided by 13. The cosine of phi is 5 divided by 13. So yeah, it matters which order you enter them into your calculator. Okay, we're basically always going to be saying, here's our angle all the time. In an AP physics course, yes, we'll give you this angle instead sometimes. Say, oh, it's 30 degrees from the vertical. Well, that would be this angle. This one is 30 degrees from the horizontal. Okay. All right, so there's that first little one. Let's try another one. Just some random numbers. What if I say the hypotenuse, I'll call it r this time. So this is example 2. Let's say that the hypotenuse is 32.0 meters per second. Ooh. And let's just make up some crazy angle and say, oh, it's 17.5 degrees. Now I'm going to ask you, what is the x component of this velocity? What is the x component of the velocity where the hypotenuse, if you like, I guess I can call this v. They would call this v initial in a physics problem. And this is the side that this is the x component of the velocity. So this is terrible notation on my part, right? Oh well. Calculate, please, using trig. If I'm giving you the hypotenuse and I'm giving you the reference angle, I want the adjacent side. I want the adjacent side What do you get when you try to use it on your calculator? Random volunteer is Daniel. And I was going to talk while you were calculating, but go ahead, speak. Right. That's why I have job security. Now, I'm wondering, Joseph, can you guide him on what to put into his calculator? Let me caution you, students. This is the hypotenuse. And the hypotenuse is always, 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 without exception, the longest of the three sides of a triangle. So if 32.0 meters per second is the longest leg of the right triangle, should you happen to get an answer that is greater than 32, you should say to yourself, uh-oh, I have done a math mistake. All right. Now, the way you said that, I'm just going to regurgitate it in my own words. Here's what I would say. The cosine of the reference angle is the ratio of the adjacent side divided by the hypotenuse. In this problem, I want to solve for the adjacent side. To get it all by itself, I would multiply both sides by the hypotenuse. So what that will look like is the adjacent side is equal to the hypotenuse times the cosine of that reference angle. All right, Daniel, I'm standing by for your calculated result based on my excellent teaching skills. Tony, are you down to just one device now? Okay, my screen is not cooperating with me then. Daniel, I'm standing by. Yeah, you listen to the other guy too much. Whoa, that is a new record. 560. That is impressive. I didn't know you could get to that big of a number starting with this stuff. You are talented. Okay, Daniel, look up here for a moment. Do you understand how I came up with this? Okay, let me do this line one more time. What I gave you is the hypotenuse. Oh man, you know what? Here's our 3-minute break. Go ponder your accomplishment there, and we'll come back in 3 minutes. Recording. All right, once again, we're back from our 3-minute break. Just at the end of our break, Well, let's continue on. I gave you a hypotenuse of 32 meters per second, a reference angle of 17.5 degrees, and the question was, what is the x component of the velocity in this case? The relevant trig function would be the cosine function, the ratio of adjacent to hypotenuse, the adjacent divided by hypotenuse. So I wrote the cosine of the reference angle is the ratio of the adjacent side, which we don't know, that we want to figure out, divided by the hypotenuse. To isolate the adjacent by itself, I multiply both sides by the hypotenuse, so it cancels on the right, and on the left, we have hypotenuse times the cosine of reference angle. So here I wrote it one last time, kind of cleanly. I said the answer that we want, the x component of the velocity, is equal to the hypotenuse, which was 32 meters per second, times the cosine of the reference angle, which is 17.5 degrees. All right. Now, Daniel, what do you get as your answer? All right. And Jacob, do you agree with that one? Oh, man. So we have a discrepancy. And now I have to decide which pattern am I going to go with? Ray, what do you get? Don't forget to unmute. Well, no units. Ouch. This was a velocity. So meters per second. 30.5 meters per second. Daniel, Jacob, or Joseph, whoever I called on, uh, how do I get you students to get this answer? Daniel, at least you're below 500 now. That's tremendous improvement. What brand calculator are you using? No worries. No worries. All right. So on your online calculator, for example, this thing is annoying me. What did you type in? Okay, okay, I'm typing that in on Google search, and it's working in units of radians. So my Google search says the answer is 7.02. Yeah. Now there's a button on this website where I can click on degrees. Well, yeah, Lord Google knows how to take care of us. So now I'm going to type in 32 times cosine 17.5, close parentheses, equals. Ta-da! Got it? Me too. All right. Now, after this simple warm-up with just two math problems, see how it's taken all period to do two math problems so far? Ouch! We're going to apply this to physics, kids. Physics. I have a box. And the box has a mass of 30 kilograms, 30.0 kilograms. And I'm going to apply a force to this box. This applied force has a magnitude of, how about 100 newtons? Woohoo! At an angle of 23.4 degrees. Oh my goodness. This is the sort of physics problems that we used to have our students struggle with every year. So now my question is, what is the x component of this applied force? So here I'm going to just draw the force again, remind you that the hypotenuse is 100 newtons, and it's not an angle drawn to scale very well. The angle is 23.4 degrees, and I want the facts, meaning I want the x component of this applied force. I call that the facts. Oh, just give me the facts, kids. Just give me the facts. All right. Our next winner here is Zara. What do you get? I'm still standing by. I'm actually pretty happy with this technology going the way it's going. I'm able to record my webcam. No units? Harshis, do you agree with that? As do I. 91.8 newtons, because this is just like the previous problem. I'm asking for the adjacent side. But now, let's upgrade. I want to have you also calculate the phi, the y component of the applied force. Ah, I always think Faraday when I write phi, but okay. Calculate the y component of the applied force. As a hint, it should be less than 100 newtons because the hypotenuse is always the largest value. All right, our next volunteer is Tony. What'd you get? I'm still waiting. Um, Tony, I'm asking if it's over 500, then you should stop having Daniel be your tutor. Okay. Well, little review. To get the adjacent side, we use the cosine function. And now I'm asking for the opposite side. If I knew the ratio of the adjacent side, now in this problem, I do. You could say that I have come up with the adjacent leg. So you could use that information. I myself would have just used the original values because this 91.8 newtons is ever so slightly rounded off. It was actually 91.77546257 dot dot dot. So just to have it be slightly more precise, I would have used the original values and then the trig function that relates the opposite side to the hypotenuse. For the hypotenuse, that is correct. Students, raise your hands if you have the answer and you're just waiting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, hands down. Interesting. Josh, do you agree with that? Uh-oh. In that case, you have to offer your own value. Oh, man. Well, that's what I got as well. 39.7 newtons. Now, 40 point something might be due to rounding errors if you had used the 91.8 newtons. Maybe. I myself would have solved this problem by saying the sine of the reference angle is the opposite side divided by the hypotenuse. So the opposite side is equal to the hypotenuse times the sine of the reference angle. And in my calculator, I would have typed in 100 times the sine of 23.4 degrees. Tony, get it? Yeah, okay. Errors happen. Let's do a physics problem now, an actual physics problem. I have a box, and this box has a mass of, oh man, let's bump it up some more, 50 kilograms. And I apply a force acting up and to the right. And by the way, Josh, you can go ahead and mute yourself. The applied force has a magnitude of, oh gosh, we're up to 200 newtons now at an angle of 32 degrees above the horizontal. But wait, there's friction. Yes. And the friction is, oh, about 62 newtons. So I'm writing 62.0 newtons. This is like the homework that I'm assigning over the weekend. If I want to complete the free body diagram, Tanusri, what should I do to make this a complete free body diagram. Okay, your audio is very low in volume. Can you speak up? What are you doing, child? Are you typing in the chat? I can hear you now. Okay, I'm drawing the force of gravity. Okay, Fabian, do you agree with that? Are we done? And how long should I draw that? Ah, and that would be a mistake. So I'm going to try to teach you right now in our closing minutes why the normal force is shorter than the force of gravity. Yikes, the normal force is going to be shorter than the force of gravity. Let's have you learn why. We're going to take the applied force and resolve it into its facts and its phi. So we're going to take the 200 newtons that's at an angle of 32 degrees and calculate the x component of this applied force and the y component of this applied force. All right, first step, what is the x component of the applied force? The hypotenuse is 200 newtons. The angle of the is 32 degrees. And I'm asking you, what is the length of the adjacent side of this right triangle? Augustine, what do you get? And if you're using an online calculator, please verify that you convert it to degrees, or set the mode for degrees. And Katie, do you agree with that? Well, I'm sad because I did not get that result. I'm going to call on Jaden. What did you get? Well, I'm going to pass you and fail everyone else. Okay, that's what I got, 169.6 newtons as well. And how? Because the adjacent side is the product of the hypotenuse times the cosine of the reference angle. So in my calculator, I typed in 200 cosine 32 because it automatically multiplies it. I didn't have to type the times. 200 cosine 32. You should do that right now and verify that, oh, yes, I get 169.6 newtons. Because if you don't, either you're wrong or I'm wrong. And if I'm wrong, Jaden's wrong. And if Jaden's wrong, we're screwed. Of course, now I want you to tell me, what is the value of the phi? Calculate, please, what is the y component of the applied force? Nathan, what do you get? 1/1000. Siddharth, do you agree with that? 11 minutes left in the period. No units? As did I. 106.0 newtons. Calculator actually said 105.9838528, which you know rounds up to 106.0. Excellent. Now, there's more to do. What is the weight of this box that has a mass of 50 kilograms? I remind you that weight is the force of gravity. The force of gravity is mass times the acceleration due to gravity. So, what is the weight of this box, Zara? The box has a mass of 50 kilograms. We assume that we're on Earth. On Earth, the acceleration due to gravity is 9.80 meters per second squared. Of course, that's in the downward direction. Units? Tyler, do you agree with that? Okay, so 490 newtons. Now, children, does the box leave the ground? You shake your head for yes or no. Okay, you students who are responding, you're shaking your head for no. I agree. That means the vertical sum of all the forces, which is, of course, the net force in the vertical direction, have to add up to 0. That means the force of gravity downward plus the normal force upward plus the y component of the applied force upward all have to add up to 0. All right, let's plug in some numbers. Negative 490 newtons. Oh man. Katie, you're unmuted. Okay. Plus the normal force plus 106 newtons add up to 0. What is the value of the normal force? Sean. I'm standing by. Repeat that. No units. And Jonathan, do you agree with that? Me too. 384 newtons. So as I claimed originally, the normal force, 384 newtons, is less than the force of gravity, 490 newtons, because of the y component of the applied force. It is partially lifting upwards on this box. So it's partially reducing the push of the table upwards on this box by 106 newtons. Next question. What is the net force in the horizontal direction acting on this box? You want me to guide you on how to figure this one out? Katie says yes. Matthew says no. Matthew's going to mute his speaker, and Katie's going to listen, right, as I draw. Okay. Horizontally, there's the x component of the applied force acting to the right. There's 62 newtons of friction acting to the left. The net force is the vector sum of those two arrows. Katie, I'm going to ask you what you get. All right, Katie? Don't forget to unmute. You don't know what we're doing. Dylan Machuca, please help her. What are we doing, Dylan? Unmute yourself. Yeah. Children. We're doing physics. Dylan, did you write down the x component of the applied force, the facts? Unmute. Dylan, do you have the value for the x component of the applied force? Do you have the facts? So, oh yeah, we did it a while ago, and the period just ended, and you guys haven't even solved for how far this box has moved starting from rest after a time of 10 seconds. How are you going to do your homework, children? Okay, someone volunteer. What is the net force in this problem? Jacob, go. And Matthew, do you agree with that? I got 107.6. But okay, zero point 0.9, zero point 0.6, we're close enough. All right, next, if that's the net force, then mass times acceleration means the acceleration in this case would have been 2.15 meters per second squared. And finally, if I start from rest, then after a time of 10 seconds, I would have gone 108 meters. I'm going to stop recording.